Math 265A. Quest to College, I'm Joe Vasta, and I'm going to cover bug 4 right now. And bug 4, we have the bug on the number line. There's the bug right there. And T is time, measured in seconds, and S is feet. Its position, its feet from the origin, and this bug is going to be walking on the number line. Well, here's the function that describes the bug in this example. It's t squared. Okay. Fill in the table. That's what they want us to do, and really it's not anything new because we've done displacement and average velocity. So let's go ahead and just do a few of them so you can see how to do this. They want the displacement from 0 to 1. Displacement from 0 to 1. Remember what that is. That is f of the end time minus f of the beginning time. So this is really what? F of 1 is 1 squared, which is 1. F of 0 is 0, 0 squared. And so this gives me 1. And so we will fill this in on the table as 1 foot. So the displacement in that time interval happens to be 1 foot. Let's go ahead and find the average velocity in that time interval. Average velocity in the time interval from 0 to 1. Why, that happens to be the displacement over the time. The displacement was 1 and the time is 1, so this is 1, and we'll do our units correctly here. We'll say 1 feet per second. So the displacement's measured in feet and the average velocity is feet per second. So basically, this is what you're doing. You're going to do this like 5 more times. And notice what's happening to the interval. The interval is getting, the time interval is getting smaller. Look, 0.5 to 1, 0.9 to 1. And then over here, if we kind of do this the other way, we have 1 to 2, 1 to 1.5, and 1 to 1.1. So I'll walk through one more of these, and then I'll fill out what I got when I actually did the calculations on this. So we'll move this back up here. We want the displacement from 0.5 to 1. This is really f of the end time minus f of the beginning time. So f of 1 is 1 squared, which is 1. F of 0.5 is 0.5 squared. You can take out your calculator and crank that out. What you would end up getting is 0.25. And so it looks like we're getting 0.75 feet for the displacement. So let's go ahead and write that right here. 0.75 feet. Okay, let's go ahead and find the average velocity. Average velocity from the time interval 0.5 to 1 is really the displacement over the time. The displacement over the time, this would be 0.75, and the time on this is 0.5. So you did that on a calculator or however you wanted to do it, you would end up getting 1.5 feet per second. And if you remember what the average velocity represents on the graph, and we're going to graph this, the average velocity represents the slope of the secant line connecting 2 points together on the graph. And the slope there would be 1.5. So let's go ahead and put this 1.5 here. I went ahead and I calculated the other ones. What I'm getting for this guy right here, from 0.9 to 1, that time interval is, look, that time interval is very short, not as long as the ones above it. I ended up getting 0.19 feet. And in terms of feet per second, it's 1.9. Now, what is happening as this time interval is getting smaller and smaller? What's happening to the average velocity? It's like 1, and then 1.5, and then 1.9. If you did 0.99 to 1, I believe I had done that somewhere, and I got like 1.9, and it was even closer to some number. It's kind of approaching a number, and so that's what they're going to ask us to do on part B of this. Okay, so let's do part A where we're filling this out. Notice that on this one, I'm going to do this one kind of backwards. I'm going to go 1 to 2, and then 1 to 1.5, and 1 to 1.1. So the time interval starts off kind of big, 1 second, and then a half second, and then a tenth of a second. And we'll see what happens as we center in on 1 from the right-hand side. See, look at that, right-hand side number is changing. So what I ended up getting for these guys is I ended up getting 3 feet displacement and 3 feet per second. We're doing this time interval, 1 to 1.5. I got 1.25 feet for the displacement and 2.5 feet per second for the average velocity. And then 1 to 1.1, this is 0.21 I've got for the displacement. And I used the calculator to get these numbers and did the similar calculations that I did for the first two. And then I ended up getting 2.1. Okay, so now here is a new word here. What is the bug's instantaneous velocity? At, not a time interval, but at a particular time, 1 second. And what they want us to do on these is they want us to guess. Now, usually in math, you're not supposed to just guess, but this time they want you to do that. And the instantaneous velocity, our guess is going to be based on what we have up here. Look, our time interval is 1 second, and then it's shorter, then it's shorter. What's happening to the average velocity as we are getting shorter time intervals and we're adjusting the right-hand side times? We are getting closer to some number, like 2.1. Where's that going to? And then when you're adjusting the numbers on the left-hand side and keeping 1 fixed on the right, look what that's getting closer to. So our guess is going to be like right in between those numbers. And this is going to tell us the instantaneous velocity. And you might have already guessed it. We're not going to try to make these like weird. Our guess for the instantaneous velocity is 2 feet per second. And that's something we're going to be interested in as we learn calculus, is instantaneous velocity. Sometimes the instantaneous velocity, they'll just call it the velocity at a certain time. Okay, we won't do that with the average velocity. When we want average velocity, we'll always use the word average velocity. But instantaneous velocity and just velocity, they're interchangeable. So that is part A and B on this problem. Filling in the table, something you already knew how to do, kind of boring when there's like 6 of them. But what they want you to do is look at average velocities and see what it's getting closer and closer to. And it looks like it's getting closer and closer to 2 feet per second. Okay, so the next problem that we're going to do is it's still going to be the same function, t squared. What they want us to do is they want us to graph the position function. So graph this right here where it says f of t equals t squared. So this is just a problem from pre-calculus or even before. So 0, 0. You put 1 in for t, you get f of 1 is 1 squared. So this is a parabola, and then 2 gives you 4. You put negative 1 in there. The input is negative 1, the output is 1. The input is negative 2, the output is 4. So this is a parabola. I'm going to go ahead and try to make this kind of neat here. Here's part of it. this is the other part right here. And so that is the question that they wanted us to answer, which was graph the parabola, graph the position function f. Okay, so we've got a few other questions. Part D, it says, draw a line that is related to the average velocity over the time interval. Okay, so I'm going to go ahead and draw that line. I'll do part D in red. Okay, so I'm going to draw a line. The average velocity from 0 seconds, remember here's time right here, 0 seconds, so we'll put that right there, a point right there, to 1 second. I'm going to put a point right here. And I'm going to draw that line. I'm going to tilt the page so I can get a nice line here. And so there is the line they asked me to draw. And a few things we want to say about that line. It connects this point with this point, so sometimes we refer to that line as the secant line. And the secant line has a slope on it. The slope of that secant line happens to be rise over run, 1 over 1, so the slope is 1. And so we got average velocity of 1 foot per second when we were in the time interval from 0 to 1. So I think that will help us answer some of these questions here. It says, how is the line related to the average velocity over 0 to 1? Well, we could say that the slope is the average velocity. And then they said, what is the line called? The line is called the secant line. So that's that, we have it right there. Okay, so now here's kind of a funny thing here. I'm going to go ahead and bend this. I'm going to have you look at this. Use a ruler here. So the slope of that line is 1. Now if I were to do the time interval from 0.5 to 1, 0.5 to 1, here's 0.5. So we have that right there, to 1, and I'd look at that secant line. That secant line, and I might not be doing it perfect, but the slope is that on that one is 1.5. And then if I went 0.9 to 1, look what's happening to the secant line. It's barely touching that graph. Maybe I should do it from this side. It's barely touching at 2 points, but that one's going to have a slope of 1.9, almost 2. And so what's happening is when we figured out what the instantaneous velocity at 2 was, we end up getting not an interval anymore, but we end up getting a line that touches this point just one time. So let me go ahead and carefully draw that line. I don't know how to do it, by the way. Here we are. And so we're going to just touch that point. See if we can do this successfully. And so this line, when it just touches one point on the graph, is called a tangent line. And so I just tried to touch t equals 1 without actually touching 2 points. You know, when I touch 2 points on that parabola, I have a secant line. When I just touch 1 point, I have a tangent line. Now notice something. What is the slope of that tangent line? Well, if you start off at this point, you climb up 1, 2, and run over 1. That has slope of 2. Now, do you remember something about 2? 2 was our guess of the instantaneous velocity at 1 second. So that's pretty cool because you go to 1 second on the t-axis, you go up to that graph, the parabola, you investigate its tangent line, draw it, and it should have a nice slope of 2, the instantaneous velocity. So let's go ahead and answer E, which actually I didn't even show you. Draw a line that is related to the instantaneous velocity at 1 second. Well, it would happen to be that purple line right there. How is the line related to the instantaneous velocity at 1 second? Well, we can say that the slope is the instantaneous velocity, or just the velocity if you like. What is the line called? Well, it happens to be a tangent line. And so you could figure out hey, what if I wanted to find the instantaneous velocity on this parabola at time 0? Well, what's the slope of that line right there? It would be 0. And what if I wanted to find the instantaneous velocity at -1 seconds? I'm trying to put a tangent line right up to this point, and it looks like it has a slope of -2. So the instantaneous velocity is -2 feet per second 1 second ago, or at -1 seconds. So this tangent line idea, this is the whole key to the beginnings of calculus. So I don't know how clear this is going to be. I am just taking a video of my laptop. The capture program on my laptop wasn't working with this program, so I just figured I'd do this. Here is the secant line for the time interval 0 to 1. And there's the secant line for the time interval 0.1 to 1. So let's get up to 0.5 to 1. So this one is 0.5 to 1, and we found that the average velocity was it was 1.5, so the slope of that line is 1.5. And then we did 0.9. So as we walk along here, what's happening to this secant line? Well, the points are getting closer, and once I get up, there we are, 0.9. So this is the secant line connecting 0.9, the t-value of 0.9 with 1. And when we continue to go closer, it gets right there, and this is called the tangent line. And so the tangent line is where it just touches one point on that parabola. But if I can move back again in terms of the sliders, let me try that, and then there's the secant line. So the secant line there's the original, and look, I could do the average velocity from -1 seconds to 1 second, and that has a slope of 0. But as I make the time interval shorter and shorter, the secant line starts looking more and more like the tangent line until it touches at that one point. Now I could have also done this. I could have put the secant line on the other side and made it at 2 at the time interval from 1 to 2. And as I get closer and closer and make that time interval less and less, look what's happening to that blue secant line. It's now right on top of the tangent line. So I thought I'd show this program to you. I hope it comes out all right. You guys have a good day.